Hi, my name is Yu, and I'm presenting Sage, a practical and scalable ML performance debugging system for microservices. This work is in collaboration with Google and students and my advisor at Cornell University. In this talk, I'll first introduce the background of our paper. We've seen a recent trend of using microservices in cloud systems. These applications have strict end-to-end service-level objectives to meet, so that the users experience the reliable application behavior. Despite of their benefits, microservices introduce several challenges in terms of performance debugging because of their scale and complexity. As with other applications of using machine learning in data center management, there is a high potential of ML in automating performance debugging as well. In this work, we present Sage, a root cause analysis system for microservices based on unsupervised learning. It relies on two main techniques. First, we build a causal-based network to model the dependency among the microservices. And second, we use the causal-based network to generate counterfactuals, which correspond to hypothetical system scenarios that help to isolate the root cause of the SLO violation. Over the past few years, cloud applications have moved from monolithic designs to microservices. Microservices split a single application into multiple fine-grained, loosely coupled, and single-concerned services that are interconnected with RPCs or RESTful APIs. These applications are governed by quality of service targets or service-level objectives in terms of latency and availability thresholds. Such thresholds exist at end-to-end application level, but not for individual microservices. The graph on the right shows the RPC dependency graph of the social network microservice in DestarBench. It is an open-source benchmark suite for microservices we developed in previous work. It consists of tens of microservices, with edges shows the dependencies between tiers. Microservices have several advantages. Specifically, they enable agile development so that developers can update each microservice frequently. They have better modularity and elasticity compared to the monoliths, since each microservice can be managed independently, and they can be tested and debugged in isolated environments. However, they also have different hardware and software constraints from monoliths, and dependencies across microservices complicate the cluster management. Given the benefits that microservices have, several cloud providers, such as Amazon, Netflix, and Twitter, have adopted this programming model. The graphs at the bottom show the dependencies between the microservices in three companies, and the services are denoted by nodes on the parameter, and the dependencies are denoted as edges. These dependencies in large-scale system makes the performance debugging and cluster management complex. Previous work on microservices, including our study of DestarBench, showed that microservices are more sensitive to performance unpredictability because each tier has more strict latency requirements compared to traditional cloud applications. In addition, the complex dependency between microservices make the performance debugging even harder than traditional applications. Hotspots can propagate through the complex network dependency graph, make both locating the root cause and recovering from the SL violation difficult. Additionally, large-scale microservices involve many trace points and data aggregation to monitor their behavior. For instance, Netflix sustains 1.2 billion time series of metrics, while Uber monitors around 500 million. Detecting the root cause in millions of time series empirically is difficult and error-prone. Therefore, it is critical to investigate automated techniques that diagnose and correct cases of unpredictable performance in microservices. Fortunately, the large number of metrics collected 24/7 makes such data-driven methods for performance debugging possible. There's a lot of previous work targeting the microservice performance debugging. CosInfer and Microscope use the PC algorithm to run a large number of conditional independence tests and identify the root cause of the poor performance. SEER, on the other hand, is a proactive root cause detect system that anticipates the culprit service using supervised learning. While beneficial, those methods have several limitations. First, the PC algorithm-based method is less practical for large-scale microservices with hundreds or thousands of nodes, since the type complexity is exponential to the total number of variables. It is also prone to statistical errors in the conditional independence tests, which leads to inaccuracies in causal graph. SEER, on the other hand, uses supervised learning and therefore requires data labeling, millisecond level instrumentation, and tracing into the OS kernel, which undermines its practicality for large-scale systems. To make performance debugging for large-scale microservices more practical, we focus on the following 5 design principles. First, while previous work has shown that supervised learning methods accurately identify the root causes, they require labeling data by injecting the noise in the system. Unfortunately, this is very expensive and impactful in production systems. So we set out to move the need for label data. Without labeling, ensuring the correlation found by an ML model between the cause and the QoS violation implies the causation is a challenging problem. Therefore, we need to build a causal model to embed the causal relationship. Second, the system should be robust to the data sampling frequency, since millisecond-level instrumentation is extremely expensive in large-scale production services. This means that we also do not rely on temporal patterns to infer the root causes. Third, it should not require kernel-level tracing, since this usually incurs high overheads in production or is altogether unavailable. Fourth, since microservices are updated much more frequently than monoliths, the system should have flexibility to adjust microservice updates. Finally, we are focusing on resource provision-related performance issues that can be solved automatically without human intervention instead of designing bugs which require human involvement. We designed Sage, a performance debugging system that follows all these 5 design principles. We now introduce the high-level overview of Sage's ML pipeline. The figure on the left is a simple RPC dependency graph between microservices, with a client, a front end which fan out the request to several services in the logic tier. Finally, the data are stored in the backend databases. We model the causal structure of the application graph with a causal Bayes network, or CBN, which follows the RPC dependency graph. The causal Bayes network is a probabilistic graphical model where the edges indicate the causal relationships. We then use counterfactuals, which examine the performance under different hypothetical scenarios to find the root cause of ASL violations. Those are generated using graphical variational autoencoder, or GVAE, which consists of several variational autoencoders according to the structure of the CBN. The GVAE takes the measured latency and usage metrics as inputs and generates the counterfactual latencies, assuming a subset of inputs had been acted upon, changing its original value. Finally, the microservices and resources that hypothetically resolve the performance issues if they had been acted upon are identified as root cause. As I mentioned earlier, causal Bayes network is a commonly used probabilistic graphical model to capture the causal structure between a set of nodes, where the edges indicate the causal relationships. The reason why we use a CBN is that it's a structural tool for causal inference that factorizes the complex cause-effect relationships between all variables, and it offers a graphical representation that is reasonably interpretable and easily explainable. We define several types of nodes in the CBN. The graph on the right-hand side is the simplest example of a CBN with just 2 microservices. We collect the service, node, and network level metrics for each microservice and network channel, such as CPU, memory, and disk utilization, network bandwidth, and so on. We name these as X nodes. We also collect the client and server-side latency, request and response network delay for each RPC, which are denoted as Y nodes. Finally, we include latent variables, or Z nodes, for each service and network channel to model the unobservable or immeasurable factors that also have impact on the end-to-end performance. Since there are many latent factors, we assume the latent variables to follow a multivariate Gaussian distribution. The X nodes are assumed exogenous to the model, and thus without any cause. The Y nodes are determined by their X and Z nodes and the Y nodes of the child RPCs, and the Z nodes are partially determined by the X nodes. The paper includes the detailed rules we use to build the CBN. With the causal Bayes network, we can then infer the root cause of the ASL violations using structured counterfactual queries. When determining the causal effect, a counterfactual query asks for the hypothetical end-to-end latency of the service if some metrics had been normal. The root cause are the metrics that hypothetically resolve the end-to-end performance issue. This is a simplified CBN between 2 services as before. In this case, assume that the end-to-end latency, which is Y0, is above the SLO, and we need to figure out whether the CPU utilization of service A or service B is a root cause. In order to do that, we compare the current y0 with its two potential values in the counterfactual world. Imagine there is a counterfactual world where we can keep all conditions the same as what they are in the real world, but set the CPU utilization of service A to its normal state. If this doesn't help to reduce the latency of y0, the CPU usage of service A alone is not the root cause for the performance issue. On the other hand, in another counterfactual world, if we do the same to the service B and the latency of y0 reduces below the SLO, we can then conclude that service B causes performance degradation. Creating such counterfactuals in the real system is impractical and potentially harmful to the performance. Therefore, we use generative model to generate counterfactuals at any given state. Among all generative models, we find the variation autoencoder-based model most suitable for the Bayesian networks. Conditional variation autoencoder, or CVE, is an extension of variation autoencoder. It contains a prior network to learn the prior distribution of latent variables given the current performance metrics, an encoder to learn the posterior distribution of latent variables given the performance metrics after observing the latency variables, and a decoder that reconstructs the input latency with the latent variable sampled from its posterior distribution. The three networks are implemented with multi-layer perceptrons. During the training phase, we're trying to minimize the reconstruction loss plus a KL divergence regularization term to prevent much information gain of the posterior distribution from its prior distribution. Instead of using a single large CVAE to represent all services and RPCs, we factorize the model according to the CBN graph to form a graphical variation autoencoder, or GVAE. This contains many cascaded CVAE fragments, each of which models a single service, network channel, and RPC. The loss function of the GVAE can be computed to be the sum of the CVAE fragment. In each CVAE fragment, we have one encoder and one prior network for each service and network channel, and one decoder for each RPC. The connections of decoders are determined by the information flow in the CBN, which can be inferred from its structure. There are several benefits from using a GVAE. First, it prunes the connections to enforce the network to learn exactly what the causal network indicates. Therefore, it is much easier and faster to train. Second, with a structured model, we can easily tell how latency is propagated from the backend to the frontend. Finally, unlike when having a single large CVAE, when a microservice changes, only a small subset of CVAEs need to be retrained, allowing faster convergence. To detect a root cause using GVAE, we first learn the distribution of latent variables from the encoder during training. Then, we calculate the normal values of all metrics and latent variables as the median values among all traces whose end-to-end SLO is satisfied. And then, we do a two-level intervention for locating the root cause. As is shown in the simplified example with two services, we first intervene all metrics and latent variables of each service iteratively until we find one or multiple services that can counterfactually solve the end-to-end performance issue. And then, we do the same to each resource and latent variable of the culprit services to locate the root cause resources. The counterfactuals are examined in parallel to accelerate the inference. Microservices are frequently added, removed, or updated in the system. During retraining, the GVAE only needs to retrain the neurons of the upstreaming services that are affected by the updates. For example, in a three-service chain, if we add a service D between B and C, we only need to add neurons for service D and update the neurons for the upstreaming A and B, keeping C unchanged. If we remove service B, we need to remove all neurons of B and update the neurons of A. If we update service C, since it is a leaf service, we need to update all neurons on the path to the frontend. We now show the system implementation of Sage, running on multiple physical nodes in large-scale cloud system. We use Jaeger and Prometheus to monitor the services, containers, and machines, and collect the traces and performance metrics. The data collection pipeline samples the data from the monitor's databases, preprocesses, and normalizes the data. We use PyTorch to implement the GVAE model. This implements partial and incremental retraining, which allows the system to reconverge quickly after an update. After locating a root cause, Sage dynamically scale up or out containers, implement cached partitioning, or network bandwidth partitioning to resolve the performance issue depending on the bottleneck resources. We evaluate Sage with two synthetic Rift services, a long dependency chain and a fan-out service, since all microservices are combinations of these two. And we also evaluate it with three end-to-end applications from Desktop Bench, implementing a social network, a media service, and a hotel reservation site. We run experiments on both local cluster and Google Cloud. We choose two auto-scaling methods and an offline oracle that has full offline knowledge of the resource and performance characteristics of each microservice as baselines. We also compare the performance of Sage with prior work, such as CoSinfer, Microscope, and Seer. First of all, let's look at the accuracy of detecting the root cause for Sage and other methods. We inject different sources of resource contention and randomly select microservices in order to obtain the ground truth for validation. In general, Sage has 88% to 95% accuracy across all 5 applications. Take social network, for example. The accuracy of Sage is much higher than 3 baselines, as the auto-scaling systems has no knowledge of impact of dependency between microservices and simply use utilization as a proxy for performance. Compared to CoSinfer and Microscope, the accuracy of Sage is higher, and this is because both systems experience incorrect causal relationships in their causal graphs due to statistical errors of the PC algorithm. Sage and Seer have similar accuracy. Sage is designed for improving the practicality rather than accuracy, since it uses unsupervised learning and much less training information than Seer. Because of this, Sage is much more robust to missing or unavailable instrumentation in individual microservices, while Seer's accuracy degrades quickly when instrumentation is removed. This animation shows how Sage and other methods resolve resource-related performance issues in real time. The x-axis is time, and the y-axis is end-to-end 99th percentile latency. We injected 10 resource-related faults to the social network, which are labeled with cross marks in the animation. Because of the high accuracy, Sage can resolve the issues quickly, and other methods either do not detect the issue altogether, taking a long time to find the root causes, or identify the wrong cause, allowing the performance to validate the SLO for a long period of time. We now focus on what happens when microservices are updated. We perform different changes to social network, including adding new services, removing and updating existing services. Incremental plus partial retraining, which is used by Sage, has least accuracy drop and fastest convergence rate than retraining from scratch and only using one of the 2 optimizations. Taking update A, for example. Comparing the orange curve with the green curve, we can observe that part of the advantage comes from the incremental retraining because we reuse most of the neural network parameters from previous training. Then, compare the blue curve with the orange curve. Partial retraining further helps to reduce the accuracy drop and improve the convergence rate because it only updates the essential subset of neurons in the network. Finally, we run Sage with social network on 84 nodes on GCE with at most 10 replicas for each service. We compare the accuracy and training and inference time to that in local experiment. The experiments on GCE are running with around 6.7 times more containers than the local runs. The accuracy is comparable with the local runs, and the training and inference time is around 20% and 27% higher, which increases significantly slower compared to the increase of cluster size. The high scalability is because instead of having each replica in separate dimension of the input data, we aggregate data across replicas into one distribution. In conclusion, we have showed that performance debugging for microservices is challenging due to complex dependencies between microservices. To address these challenges, we built Sage, a root cause detection system based on unsupervised learning, which relies on causal-based network for modeling the causal relationships and counterfactuals to detect the root cause of SL violations. Across a set of representative end-to-end applications built with microservices, we showed that Sage achieves high accuracy in detecting the root cause and quickly recovers the performance. It is also flexible to service updates and scales well in large-scale deployments on Google's public cloud. Beyond resource-related performance issues, similar techniques can also be applied to design bugs and security threats. Thank you very much for listening, and questions are welcome at session 4 Q&A panel.